Good day, people. Today we'll be talking about engineered cementitious composite, or known as ECC. So before we get into this topic, let us delve into some background story. So as a general knowledge for civil engineers, normal concrete is strong in composite strength but poor in tensile strength. The inventor of ECC, Victor Lee, argued that most infrastructure failures are due to insufficient capacity to carry tensile load, even though reinforced concrete is used. Therefore, there is an incentive to improve the tensile capacity of concrete, particularly when the buildings or infrastructure in question are to be built at seismic area. So what is ECC? ECC is a mortar-based composite which, upon hardening, it will form a concrete that is more flexible than normal concrete. EEC is 50 times more flexible, 40 times lighter, and has good energy absorbing properties. So the key ingredients to create the ECC are superfine silica sand, cement, high range water reducing agents, or known as superplasticizers in some countries, polyvinyl alcoholic fiber, or PVA fiber in short, and last but not least, the most important one is water. The significant characteristic of ECC is that the powder content is 2 to 3 times higher than conventional concrete. This is because we do this to achieve rheological control to disperse the fiber easily, and to achieve matrix toughness control for strain hardening behavior. The reason is that strain hardening is possible by limiting the matrix fracture toughness such that multiple cracking could occur before reaching maximum fiber. Hence, in the ECC mixture, you will not see any coarse aggregates in it. A major drawback with the ECC is that it has high cement content, as we have mentioned earlier. So during hydration, because of this high cement content, you will produce a lot of heat. And on top of it, since you are requiring a high amount of cement, you would require these kilns to increase the cement production. And what is worse is that the cement production is one of the major sources of global greenhouse gas emission, including some nitrate oxides, particulate matters, and other pollutants. With that in mind, researchers have come up with some innovations to alter the design mix of the normal ECC. Some known industrial byproducts that can be used to replace cement are fly ash, ground granulated blast furnace slag, and rice husk ash. These byproducts contain a significant amount of silica, which is the most important source to form pozzolanic reaction, and it is important for matrix bonding. The case of the effectiveness of fly ash in ECC has been conducted by Wang and Lee in 2007. They have concluded that a high volume fraction of fly ash could achieve high tensile strength capacity, but the sacrifice would be the PVA fiber matrix interface bond and the matrix toughness. The case of using slag as the cement replacement has been studied by Lim et al. In 2012. From the first and the third figure, The results have shown that the general trend for the increasing slag content in ECC is that the compressive strength development and displacement capacity under tensile loading are better than conventional concrete C60. However, as we have seen in the second figure, that is not the case. The tensile strength of slag-ECC is marginally better, only at around 38 days. And in the long run, the tensile strength decreases.
So in these sections, I'm going to discuss about some examples regarding the application and performance of ECC on the actual practice. So there are four main areas that will be covered in these sections, which is building, bridges, roads, and water infrastructures such as dam. So first, I'm going to start with the buildings. So normally the buildings near to the coastal areas are generally vulnerable to the environmental driven corrosion. So because as we all know, the atmosphere in this coastal area normally has a higher salt content compared to the inner land. So this high salt content will normally triggers the reinforcement of the external wall to start to corrode. So when the reinforcement corrodes, it will cause the steel within the wall to rust and will increase the volume. So this increase of volume will cause an expansion and creates a tensile stress within the concrete, and which will eventually cause the wall to crack and start to spoil. So one of the methods to overcome this spalling issue is to apply a thin layer of ECC on the cracking zone. So because ECC normally has a higher ductility and it is bendable, it's not like the conventional concrete that are more stiff and cannot be bent. So due to the inherent properties of ECC, it actually allows the cracking zone to expand without spalling from dislodging. Therefore, less maintenance will be required if we use CCC on the external wall surface, and the maintenance will be lesser over time. So next we move to the bridges. So in the conventional bridges, expansion joint is actually quite common because the reason why there is an expansion joint is to allow the movement of the bridge deck that are triggered by the fluctuation of the temperature of the surrounding due to the contraction or expansion. So however, this expansion joint can cause some issue. So one of the issue is the leakage of rainwater and salt into the movement joint. So throughout the continuous leakage of the substances into this movement joint, it will cause the bridge deck to deteriorate over time. So another issue with this movement joint is the debris accumulations. So when more debris has been accumulated in these movement joints, it will eventually affect the effectiveness of the movement of the bridge deck that are triggered by the environmental temperature fluctuations. So an expansion joint will require a more frequent maintenance. So one of the methods that can be used to avoid the problems that is associated with the movement joint is to substitute the conventional bridge concrete pavement with EEC link slab. So because the EEC has a higher ductility, and therefore the expansion joint can be omitted. So besides, EEC link slab can also accommodate the deck movement that are induced by the thermal stress. So next we move to the rods. So the issue with the rods is actually quite similar to the bridges, which is the common issues that is associated with the joint, such as the infiltration of the substances such as debris and water into the movement joint. So for some of the block that utilize a concrete pavement, noise is one of the main issue, because because of the car movement, it will actually create a vibration and will increase the height noise level to the surrounding. So in order to reduce the noise issue, one of the methods is to apply the ECC on the concrete pavement. Because inside ECC there is fibers, and then these fibers can actually disperse the vibrations and absorb the traffic vibration, which can eventually reduce the noise level. So by using the ECC on the rock pavement, it tends to be more durable and less maintenance also required. And last, we move to water infrastructure. Um, so in this example, we look into a dam. So one of the most common issue with the dam is the water leakage issue and concrete spalling, because the main reason why we use dam is to accommodate the water. So if there is a water leakage and they will actually reduce the efficiency of the dam. So the typical method to overcome this joint cracking is by applying a new layer of concrete on the cracking zone. However, reflective cracking is one of the issues that will occur after applying a new concrete. So, but what is reflective cracking? So, reflective cracking is actually an additional cracking that occurs on the existing cracks. So, in next slide, we'll show some examples of the reflective cracking. So picture A is the example of the reflective cracking, so which has a bigger cracking width. So in order to mitigate this reflective cracking issue, we can use a EC to spray on the deteriorated cracking surface. So by applying a layer of ECC on this cracking zone, reflective cracking will be avoided lah. So instead of the reflective cracking, micro cracking was observed after using EC. So from the diagram B, you can see that there is basically the micro cracking, which occurs after applying ECC. So by comparing A and B, reflective cracking and micro cracking, we can see that the cracking width is actually a significantly smaller compared to the reflective cracking. So the reason of this micro cracking is because the EEC is able to distribute the tensile stress from the reinforcement. So by using this EEC, the reduction of water and dirt permeation can also be achieved in this dam. So that's it for our presentations on this bendable concrete, or also known as ECC, Engineered Composite Concrete. Thank you very much.